Have you ever wondered what's going on when you ride a roller coaster? You might think it's magic, but it's actually physics. Today we're going to explore the science behind your favorite ride. To understand what's going on at the top and the bottom of the roller coaster, we need to understand forces, which is a central part of Newton's laws of motion. Normal force is the force exerted on an object from a surface that is perpendicular to the object and the surface. Gravitational force is the force of gravity on an object and can be calculated by multiplying mass times gravity, which is approximately 9.8 meters per second squared. This isn't your average motion problem. This is a circular motion problem. You might recall with other types of problems, like balanced forces or unbalanced forces, we'd be using sum of the forces is equal to 0, or sum of the forces is equal to mass times acceleration. This problem, we will not be doing that. Instead, we'll be using a special equation. Sum of the forces is equal to mass times centripetal acceleration. You might be wondering, what is centripetal acceleration? You might recall that acceleration is found by dividing the change in velocity over the change in time. Centripetal acceleration is found by multiplying mass times velocity squared over the radius. Back to our roller coaster. Because we're dealing with circular motion, the net force must be directed towards the inside of the circle. This means that at the top of the roller coaster, the Fg must be greater, while at the bottom of the roller coaster, the Fn must be greater. Now let's use our equations to solve for the normal force at the top and the bottom of the hill. If you'll recall our equation from earlier, the sum of the forces is equal to m times the centripetal acceleration. We can simplify that to mv squared over r. The force of gravity is greater at the top of the hill, so we can have Fg minus Fn is equal to mv squared over r. Simplifying that will give us Fn is equal to mg minus mv squared over r. At the bottom of the hill, we do the same thing. The sum of the forces is equal to mac, except Fn is greater at the bottom of the hill, like we determined earlier. So we get Fn is equal to mg plus mv squared over r. This sign is an important difference because it makes the Fn less at the top and greater at the bottom, which is why we feel lighter at the top and heavier at the bottom. Next time you're ever feeling bored on a roller coaster, remember these equations, and remember the invisible forces of physics that keep us from falling at the most important times in our lives.